We're here at lecture 3D, and we're going to continue our discussion on solubility here and take a look to see how the Chatelier's principle comes into play with solubility equilibria and also the common ion effect. So in our previous course, we took a look to see how adding a common ion to specifically a common ion on the product side can suppress the reaction moving in the forward direction. So if we had an acid or a base and we added something that just added something into the product, it would suppress the dissociation of that acid or a base. And the same effect applies to solubility also. So if we can just use Le Chatelier's principle for a very qualitative look to see how that might appear. We can still use our concept of Q for a more quantitative aspect here in just a little bit. So let's just say that we have a saturated solution of silver chloride. So we've had some silver chloride in water. It sat there for a while and it's reached its equilibrium and the solution is saturated. At equilibrium, we have the following reaction set up. We have AgCl solid going to Ag plus Cl minus. We have a KSP value equaling concentration of silver ion times concentration of chloride ion. Well, what would happen if I added a source of Ag? Well, if I made my concentration of Ag plus go up, then it's going to force the reaction to have to move back in that direction. What if I added a source of Cl minus? Well, if I added a source of Cl minus, the exact same thing would happen and it would drive that reaction back to the solid. And what that does is it makes the solid less soluble in a solution that contains a common ion to one of the products. The reason it does that is because the reaction at equilibrium, when something is added to something at equilibrium, it's thrown out of equilibrium. And here, by adding either a source of chloride or a source of silver, if I'm no longer at equilibrium, then I have to do a Q calculation. And remember, the calculations are exactly the same. It just means we know we're not at equilibrium. So if I calculated after the addition of some Ag, my concentration of Ag times Cl would be greater than my KSP. And so if it's greater than the KSP, then that reaction has to shift left, create more solid, and so I would have less Cl than before. So I would still have more Ag plus than before, but the molar solubility would be calculated by the Cl, and it would be a lower value, and so my molar solubility would be less. And the same would be the case if I added more Cl. The Ag plus would have to be used to calculate the molar solubility, and I would still have a lower value of the amount of Ag plus that came from the silver chloride. Let's do a calculation and see how it actually goes. We want to know what is the molar solubility of silver chloride in pure water, so just going in water. And then I want to know what is the molar solubility in a 6.5 times 10 to the minus 3 molar silver nitrate solution. So silver nitrate is going to have silver ions and nitrate ions completely dissociated because nitrates are all soluble. So it becomes a source of silver plus. It's not a very concentrated solution, just 10 to the minus 3. That's actually pretty low. So let's see what happens here. So in pure water, I still have the exact same equilibrium. AgCl goes to Ag plus Cl minus. I have a KSP of Ag plus times Cl minus concentrations. I can do an icebox. Lots of silver chloride, no silver, no chloride. I lose X amount of silver chloride. I gain X amount of silver. I gain X amount of chloride. At equilibrium, I still have lots of solid. I'm going to have X amount of silver, X amount of chloride. I plug that into my KSP expression where I would have the KSP is equal to concentration of silver times concentration of chloride, like we have here. This is a value of X. This is also a value of X, and so I get X squared. I solve for X, and I get a value of 1.34 times 10 to the minus 5. So that is my molar solubility of AgCl in pure water. It's also the concentration of my silver. It's also the concentration of my chloride. All right, now let's check the silver nitrate solution. So in that silver nitrate, remember I mentioned that silver nitrate is extremely soluble. So a one-way arrow here, it goes to silver ions and nitrate ions. So really what I have is I have 6.5 times 10 to the minus 3 molar silver ion concentration and the same concentration for the nitrate. I don't care about the nitrate. It's not part of what's going on chemically. So let's set up another ice box for our AgCl. So for my AgCl, I still have lots of solid, but now I have a starting value of Ag plus from the silver nitrate. So I have 6.5 times 10 to the minus 3. And of course, I have no chloride because nothing has dissolved yet from the silver chloride. I'm going to lose X amount of my silver chloride. From that, I'm going to gain X amount of silver, and I'm going to gain X amount of my chloride. And then I got to add everything up. Still got lots of solid there. Concentration of my silver is 6.5 times 10 to the minus 3 plus X, and then my chloride is just X. Okay, remember, my chloride, all the chloride comes just from the silver chloride breaking apart. Concentration of my silver comes from the silver nitrate plus what comes from the silver chloride breaking apart. We set up our KSP expression. We have 1.8 times 10 to the minus 10. We have the concentration of silver, 6.5 times 10 to the minus 3 plus X, times concentration of chloride, X. When we solve that equation for X, I get an X value of 2.77 times 10 to the minus 8 molar. Notice that this is about 1,000 times less soluble than it was in pure water. And that's due to just this little bit of silver nitrate already in there. So the reason that that happens is because I have a source of silver going into that solution, which means I can't have as much chloride coming from the silver chloride. And so the molar solubility of that silver chloride is suppressed. Now, there's a lot of precipitates that contain ions that are conjugate bases of weak acids. And that small amount of conjugate base can react with any H3O plus coming from an acid that happens to be in solution. And if it reacts with that H3O plus, it will most likely be removed from the equilibrium because it turns into something different. And so what this does is it can cause more precipitate to dissolve because now in removing one of the products and turning it into a different compound than is in the equilibrium expression, then the reaction says, well, I just lost one of those compounds. I have to dissolve more. And so it causes solids to be more soluble. So the solubility of these types of salts is much greater in acid than in water. Again, one of the ions has to be a conjugate base of a weak acid in order for this to happen. So let's take a look at copper carbonate. So copper carbonate has a 1-to-1, so just CuCO3 goes to copper 2 plus carbonate 2 minus. Its KSP is going to be concentration of the copper ion times concentration of our carbonate. Now, when we add acid, okay, acid's going to come in the form of H3O plus, so it can just be any old acid that we're adding in. If it's an acid, it's going to have H3O plus in it. It's going to react with the carbonate ion, CO3 2 minus, and form the bicarbonate ion. You have a conjugate base and an acid. So this is going to form water. The conjugate base is going to grab an H plus away from the water and give us the bicarbonate ion and H2O. Now, notice that this ion does not show up in the KSP expression. And so what happened, however, is that CO3 ion that takes place in that reaction gets removed. And so the concentration of CO3 2 minus begins to drop. And if it drops, that means that my Q value is now too low. And that means that the reaction is going to respond and say, I need to make more carbonate ion to match equilibrium. And so it's going to force this reaction to go to the right. So it's actually going to make the reaction more soluble. It's going to make copper carbonate more soluble. Now, there's also ways of removing the metal ion. However, we'll cover that a little bit later in this not in this section, but later in lecture 3.